okay, so let's recall again the single variable case. Let's recall the one variable case. Okay, if I say something like the limit of 2x plus 1 is 7 as x approaches 3, then what's that saying? You have sort of like your intuitive notion, right? That here is 1, 2, 3, right? And with heading at a height speed of 2, going up like this, right? That as your so here's your function, right? 2x plus 1. Right? As your inputs get closer and closer to 3, right? Your outputs get closer and closer to 7, right? And did we talk about the epsilon delta stuff in this class? We did. Okay, right. So recall what this really means is that given any epsilon, there is an interval (3 minus epsilon, 3 minus delta, 3 plus delta), such that if x is in that interval, and maybe not at 3 itself, then f of x, right, 2x plus 1 minus 7, is smaller than epsilon. What did it mean for the limit to be 7? It meant that if anybody placed a constraint on you on how close your outputs have to be to 7, right? If somebody says, I need you to stay within 0.1 of 7, well, you can find an interval around 3 in which those constraints are satisfied, right? If it's 0.1, you can probably just tell me by looking at it, what's the width of the interval? Maybe make it a little bit easier. If it's 1, say, somebody says, I'd like your outputs to stay within 1 of 7. Well, how close do I need to be to 3 to ensure that happens? Don't blurt it out. Think for 15 seconds. Half a minute. I'll give you half a minute. Who would like to say? Anybody? Sydney?
Oh, 1/2.
Yeah, 1/2 will do, right? One half will do. Right? As long as I stay between 2.5 and 3.5, then all my outputs satisfied, right? And if this were 0.1, then I could take 0.05. Right? Instead of 0.5, I could take 0.05, et cetera, right? So, right, this is what limit being 7 meant, that no matter how tight a tolerance you're given, there is a place around 3 in which that tolerance is satisfied. Okay. And so that's actually the thing that we're going to, the definition we're going to use when we go to higher dimensions. Okay. So let me just stop for a second. Is that okay? Is everyone all right with that? Okay. Melissa, are you okay?
Yes.
Really?
Yes.
Okay. Okay, great. So here's the definition in higher dimensions, right? So suppose you have some function on R2. For simplicity, let's use R2. So a function of 2 variables. We say the limit of fxy is L as xy approaches AB if given any, like this, if for each number epsilon greater than 0, there is a corresponding delta greater than 0 such that something happens, right? What should I write? What do you think I should write down here? We say that the limit is L if given any epsilon, there's a corresponding delta, so that if, how should I modify it? How do you think I should modify it? Right. In the first picture, right? Somebody gives you a pair of lines here, and you find an interval in which everybody in that interval, excluding the middle, stays between those pairs of lines. Right? Okay. So now we've got a function on R2, right? And we've got a point AB, right? And we have some value L, right? So L is a height. Right? L is some height. Right? Okay. And we're saying that the limit as f as xy goes to AB is L. How should we modify it? Does anyone have an idea? Anyone want to make a guess? Alana? No? Don't know? Okay. So here, anybody? No? Okay, so here's how you do it. You say, well, so that if the magnitude of xy minus ab is less than delta and greater than 0, then f of xy minus L is less than epsilon. Okay, so this is basically the same thing. Let me show you how it looks in one dimension. So if I take this picture here and I spread it out, here is C and here is L, and here's my function f. Okay. The definition looks like this. Given any tolerance around L, there's an interval around C where everybody, excluding maybe C itself, gets mapped inside there. Okay. Now the picture here is going to be like this, right? You're going from R2 to R, right? And here's our L, and here's our AB now. Okay. And what we're saying is that given any tolerance around L, there is a, well, what is this thing? What is this thing? The distance of xy to AB is less than delta and greater than 0. What is that?
Circle.
It's a circle, right? It's a disk. So there's a disk around AB. There's a disk centered at AB of radius delta, right? In which everybody gets mapped inside here except maybe the middle. Okay. So that's the difference. As you, it's sort of, like how you think you ought, how you would expect, how one might expect it to be. Okay. So given any interval around L, given any tolerance around L, there's a disk around AB that gets mapped inside that thing, right? And the picture here is going to be like this, right? You're going to have L plus epsilon, L minus epsilon, and these will be planes now, right? So you've got a pair of planes, right? One above L and one below L. And what you're saying is that given any such pair of planes, there's a disk around AB in which all the values lie between those two planes. Okay. So that's the definition of limit. Okay. Does that make sense? You all seem kind of even more You were a quiet class in general, but now you seem more quiet. Are you okay? Is everyone all right? Okay, close your eyes for a second. Who would raise a finger if you'd like the lecture to go faster? Raise a finger if you'd like the lecture to go slower. Okay. Okay. Open your eyes, please. Thank you. Thank you. Okay. Okay. So, okay. Well, maybe this can be made a bit simpler if I give you an example. Okay. So here's a good example from the text. Okay. So they say, well, show that the limit of 3x squared y over x squared plus y squared is 0 as xy goes to 0, 0. I should say that the result of the poll is that most everybody was okay, but there were a couple of people who wanted to slow down slightly. To slow down. Okay. Show that the limit of this thing is 0 as x goes to 0, 0. Okay. So okay. So let's think. What does that mean? What does that mean? What does that mean? Well, that means that given any epsilon greater than 0, we want a delta so that if the distance of xy to 0, 0 is less than delta and greater than 0, then 3x squared y over x squared plus y squared needs to be less than epsilon. Okay, so we're trying to show that the limit of this thing is 0, right? We're trying to show that the limit of this thing is 0. And what does that mean? That means that if somebody wants us to stay close to 0, we should be able to find a place where that happens, right? So we want to be able to find a place, right? So this is the place we're looking for. We want to be able to find a place where this thing is small, right? We're trying to show that the limit is 0. We're trying to find a place where this thing is smaller than epsilon, in absolute value smaller than epsilon. In other words, trapped between epsilon and negative epsilon, right? The two planes at height epsilon and negative epsilon. Okay. Okay. So So magically, so I'm going to explain it in a sort of a mysterious way first, and then I'll explain how we figured it out later in a second. Okay. Magically, take delta to be epsilon over 3. Okay. So somebody wants your values to stay between epsilon and negative epsilon. And I'm saying that as long as you take delta to be epsilon over 3, then all your values in this disk here, excluding maybe the origin, will stay between the planes. Okay. So magically, this is going to be the answer. Delta, a radius of epsilon over 3 will do. Okay. Why does this work? Why does this work? Well, right, if the absolute value of x minus y minus 0, 0 is less than epsilon over 3, then if we look at 3x squared y over x squared plus y squared, we see that this thing is smaller than, let me write it like this. This is the same thing as 3y times x squared over x squared plus y squared. Right, I'm just factoring the 3y out. And this thing is smaller than 3y. Right? Because x squared over x squared plus y squared is always smaller than 1. Right? So so this product is always going to be smaller than 3y. And that's smaller than 3 times the magnitude of x plus y, the magnitude of xy. But the magnitude of xy is smaller than epsilon over 3, right? So this thing is smaller than 3 times epsilon over 3, which is epsilon. And so what you see is that, look, lo and behold, right? If as long as xy is within epsilon over 3 to 0, then 3x squared y over x squared plus y squared is smaller than epsilon, right? The outputs all lie between these two things. Okay. So we found the delta that works, somehow mysterious. This is maybe tricky, so I don't know. It's probably kind of unfamiliar. So please ask questions. Please ask questions. Say, I'm completely confused, or like, are you speaking English, or do you actually speak English? As to sort of maybe tell a joke, maybe. When I first started teaching in graduate school at the University of Chicago, I was like 22 or something like that. And then one day, one of the administrators came over. She was like the boss of all the graduate students. She said, "Winston, I have to talk with you." Put her hand on my shoulder. She said, "A student came to me today, and the student said to me that he had to switch out of your section because he could not understand your accent at all." And she said, I told the student, I know Winston O, and he doesn't have any accent, but the student insisted, no, he has a very, very strong Chinese accent. No, he didn't say Chinese, he has a very, very strong accent. I'm like, okay, let's see, I was born in North Carolina. Is it my southern accent that still lasted after so many years? And so in the end, she let the student switch out of my class because didn't understand my accent. Okay, questions? Actually, there actually is research about how people's how visual perception of influences your oral perception. So they show a picture of somebody clearly from mainland China, say, and they dub over it a native speaker's voice, and people hear a Chinese accent. And conversely, they take a white person, say, and dub it over with a Chinese person's voice, and the people hear no accent. Amazingly, right? So that it could be that was what was going on. Yeah. Okay, go on. Or it could be that my southern accent is still showing. Yes, Peter.
How does this prove that the limit is 0 rather than some other number within the interval of negative epsilon to epsilon?
Right. So the 0 is actually here, right? So what this shows is that given any distance to 0, given any distance, you can make this thing as close to 0 as you like. Okay, so given any epsilon, right, we can, given any epsilon, given any planes centered at 0, right, we can find a place where the values stay between those pairs, right? So we can close in on 0 as far as we'd like. But you see that these things are closed on 0, not on any other point. Yeah, Paul?
How would you do that if instead of like 0, 0, the point was like 3, 2?
Yeah, so it's going to be so 3, 2. Then you'd have some other value here, and then you'll see in a second. I think it will become clearer. Although there's no routine for it. There's no like absolute way of doing it. Okay, so yeah. Other questions? Other questions? Okay. Okay. So right. So what we're saying here is that if somebody wants these two things to stay close to, if somebody wants your output to stay close to 0, if somebody wants your output to stay within epsilon of 0, well, as long as your inputs stay within epsilon over 3 of the origin here, then your outputs will stay there. Will satisfy that. Okay. Now I'm going to explain how we got the delta. Okay. Okay. Right. You don't actually do it just magically. Right. So you say, well, how does one find the right delta? A working. Okay. And the way one does it is like this. You say, well, you analyze what you're trying to control, what you're trying to make happen, right? We're trying to make this thing, right? We're trying to make this thing happen, right? We're trying to make this thing happen, and you're hoping that you can control this thing by some by the distance to 0 of xy. Okay. So you say, well, okay. You say, well, basically you run through a similar process here. You say, well, look, this thing on the left, of course I can get rid of the 0. Of course I can get rid of the 0, right? And you're thinking, okay, I'd like to control this by this thing here. And you say, okay, we're basically going to run through the same thing. We say, well, look, this thing is smaller than 3x squared plus y squared is y. Right? This thing is smaller than 1. Right? This thing here is smaller than 1 always. And I know that the y I'm going to control by y squared plus x squared square rooted. Okay. Like this, you say, well, look, if I didn't have this x squared here, then I'd have the square root of, I'd have the absolute value of y. Right? If I throw in an x squared, it just gets bigger, right? So this thing is definitely bigger than what I had there before. Okay, so I'm going to say that. I say, oh, okay, that's great. That thing actually is this xy minus 0, 0. Right? And from there, you'd say, well, okay, so that sort of gives it to me. In order to make this thing within epsilon of 0, I need to make this distance smaller than epsilon over 3. Right? I just need to make this distance smaller than epsilon over 3, and that's how I chose the delta as epsilon over 3. Right? So to ensure this thing x squared plus y squared 0 is smaller than epsilon, we just require x1 minus 0, 0 is smaller than epsilon over here. And that's how you choose the delta. But as you see, it requires some trickery, right? You need to think about this thing. It's like, oh, how do I get this thing controlled by that thing, right? Yeah, Lily.
How come you can just say jump right from the to the 3? Yeah.
From here to here?
No, from one.
From
to
here to
the-
here?
Yeah.
So this is a 3. That's the same thing here. This thing is smaller than 1, right? So that's is that okay? That this thing is smaller than 1, right? Because the bottom is bigger than the top, right? Bigger than or equal to the top, right? And then this thing here, I'm saying is smaller than that thing, right? Because this equals that, right? Which is smaller than that.
But why are you doing that?
Why am I doing that? Because I'm trying to control this thing with the distance to 0. This thing actually is the distance to 0, right? This thing is the distance to 0,
Okay.
right? So I'm trying to basically sneak in the distance to 0 somehow. By hook or by crook, I'd like to put the distance to 0 in there,
Okay.
right? And if I can, then that basically does it for me. Yeah, Laura.
What are you saying is less than or equal to 1?
This thing in the absolute values.
Okay.
Yeah, x squared over x squared plus y squared in absolute value. Okay. Ask more questions if you need. It's not at all straightforward. Right. Okay. I think I do actually speak English, although there's one part of English that I have never been able to do successfully, and that is profanity. Actually, yeah, I think as the child of immigrants, you're sort of limited. You don't get exposed to profanity or something. I can't swear with a damn. Yeah. Like even if I'm angry, I can't manage. Whereas I have friends from college who are really masterful at incorporating profanity into their daily language. Okay. So this is the game of showing that the limit is something. Okay. The game of showing that the limit of some function is something. That's one game. Another thing that you'll be asked to do on the homework, and it's not, frankly, I don't consider this to be that important, but we'll play the game. Why not? Showing limits do not exist. So that will involve this theorem, which says that if the limit as xy approaches ab is L, if the limit actually does exist, then in fact f of xy will go to L along any path to AB. Okay. So that is right. If you have your AB here, and there's some height L, what it's saying is that if you take any path to AB, along that path you should get the value. Your values should tend to L. Doesn't matter what path you take, straight lines, curved lines, whatever. Any path to AB, the outputs should tend to L. Okay, and conversely, right, if thus if f of xy tends to one value along one path, and f of xy tends to another value along another path, and these things are not the same, then you know that the limit doesn't exist. Right? Because if the limit existed, this would not happen, right? Okay, so let's do an example. Say that the limit of 6x cubed y over 2x to the fourth plus y to the fourth as xy goes to 0, 0. Does this exist? Does this limit exist? Okay. So maybe take a minute or two and see if you can find, two different paths to 0 to the origin along which the function tends to its different values. Okay, did anyone come up with something? Maybe first take a minute and turn to somebody next to you and say what you tried.
But I was just like putting just thinking about what the function does. Like when it's 0, 0, it's like it's 0 to 0.
Okay. Anyone want to suggest paths to 0? So we have this function, right? And here is 0, 0, right? Along one path, we'll probably get one value. In the end, what's going to happen is that the limit is not going to exist. Okay. Did anyone find different paths to 0 along which the function tended toward different limits? Peter, you had.
If you said x equal to y.
Okay, so along x equal y, so you're saying, well, let's approach along this line, right? The line y equals x. Okay. In that case, you get 6x to the 4th over 3x to the 4th as x goes to 0, right? The limit basically becomes this, right? But that's 2, and that is 2. Okay. So what you see is that if we let our xy's go along this line and tend toward the origin, then the values tend towards 2. Okay. And what about another line, another approach, Peter?
If you just set x or y equal to 0.
Okay. So yeah. Okay. So if we set one but not the other equal to 0, of course, let's say x equals 0. Right. So if we approach along this path, then we see that we get 0. We get 0, right? So the limit of this thing is going to be 0 over y to the 4th, right? As y goes to 0, which is 0. Okay. And so we see that there are 2 different paths along which we get different values, and so the limit cannot exist. Okay, so that's one game that you do in your homework. It's not the most interesting game, I'm afraid. I'll give you a hint. One of the problems involves approaching not along the line, but along I think a parabola or some cubic or something like that. So you might have to take a sort of an odd path into the origin to make it work out. Okay. Okay. So the rest of the section is sort of standard stuff, right? After limits, you always introduce continuity. So continuity, right? Here's the definition. If the limit of f of xy is the value as x approaches ab, xy approaches ab, it's just the value f at ab, then we say f is continuous at ab. F is continuous at ab. Right. That's to say that you're approaching AB, and it looks like you're tending towards some value, and when you reach there, you actually get that limit value. Okay. So the limit that you appear to be tending towards is actually the value of the function there. So a fact, just as in the one variable case, polynomials. Oh, sorry. I should put in another definition. So if the function is continuous on at each point of a set, we say f is continuous on that set. Okay, so there's continuity at a point, and then continuity on a set. Continuity on a set means you're continuous at every point in that set. Okay, so like continuous everywhere means that at every point you're continuous. Continuous is really a pointwise condition for us at least. So now, just as in the one variable case, polynomials are continuous everywhere. And rational functions are continuous where they're defined. So not where the origin, not where the denominators are 0, right? Rational functions, remember, are polynomial over polynomial. So where q of x is 0, where the denominator is not 0. So, for example, the function that we were looking at earlier, f of xy, being 3x squared y over x squared plus y squared, this is a rational function, and so it's continuous everywhere. Right? It's continuous at all xy, excluding the origin. Now you remember that we actually could make this thing. This thing actually had a limit at the origin. Right? So recall that the limit of this guy, as x squared, as xy goes to 0, 0, actually was 0. So if we make a new function that's this guy, and we let it take the value 0 when xy is 0, 0, then this function is continuous everywhere. Right, so our previous function was continuous everywhere except for at the origin, but it actually had a value at the origin, right? As you tended toward the origin, the value tended towards 0, and so if we just make it 0 at the origin, then it becomes continuous everywhere. Okay, so this is a function that it was tending towards the origin. But at the origin, it didn't have a value. And basically, we were just filling in the value there, right? Just like filling in the one variable case, it's just like filling in a discontinuity. Okay. Don't worry, we're almost to the end. Sorry, I know this is pretty dry stuff. Next time, I promise it'll be better. We'll talk about differentiation and tangent planes, which is actually pretty interesting. Okay, but let me finish up with something of equally exciting to the previous material, which is composition and continuity. So composition and continuity. So you have one function, f r squared to r, is continuous at AB. And you have another function which is continuous at f of AB. Then the composition is continuous at AB. So that is, the composition of continuous functions is going to be continuous. right? So the picture is like this, right? You have one function, you have f going here, and then after f, you have another function. And this first function is continuous at some point, a, b, and the second function is continuous at the output, right? Then the composition function, right? The composition function is continuous here, as you might expect. So, for example, if we look at f of xy being the natural log of x squared plus y squared minus 4, right? This is a composition function, right? You have this function, which is a polynomial, and then you have a natural log function on top of that. So this is a composition function. It's going to be continuous where it makes sense, right? As long as this thing is bigger than 0, right? In other words, you need x squared plus y squared to be bigger than 4. Right? So outside, this thing is continuous outside of the circle or radius 2. Say. Okay, that's it for today. It'll be better next time, I promise.